Transformations of graphs is a principle that will be covered in both the AS and the A2 of maths, and in large part it is going to be the same principles used in both cases. It's just the complexity of the question itself perhaps is obviously going to advance as you go forwards. And while there will be the addition of another kind of transformation in the A2, that being the modulus, that we will talk about in the second half of this video, to start off with, there are really only three main principles, each of which have an application in the x and the y-axis, so making 6 transformations in total. Let's just say we were to start with y equals fx, so fx is in turn some other expression of x, but we're using fx rather than just y equals that equation because it's easier to demonstrate what change is happening to the function in a function layout, if that makes sense. So for instance here, if we wish to do the f of minus x, let's say the transformation that we are going to do is replace every x with a minus x. So this is a lot easier to represent by doing it this way than just going through and changing all the x's individually. Well, if we were to do this, the effect this would have is reflecting in the y-axis. So basically what we're saying is if you were to take the x-coordinate 1, rather than then plotting with it the y-coordinate that would otherwise go with x equals 1, instead you would look to the y-coordinate that would otherwise be associated with x equals minus 1. What this does is that brings that y-coordinate over from the left to the right. Meanwhile, the y-coordinate that was on the right will now take its place on the left, as would happen with every x-coordinate. So everything that's on the left will go on to the right, everything on the right would come to the left. Therefore, if, say, your original graph just looks something like that, then after doing the f of minus x, it would end up looking more like this. And this is reflected in that vertical line in the middle. If instead, though, rather than putting the minus inside the bracket with the x, you put it on the outside, so it's minus f of x, this would instead mean that you are reflecting in the x-axis. So here, what's on the top will come to the bottom, and what's on the bottom will come to the top. The reason for this being that for each given x coordinates, again let's use x equals 1, you would still be looking at the y coordinate that's meant to be associated with it. It's just now that you are going to stick a minus in front of that y coordinate. Therefore, again, if we start with this same original graph shape here, now instead, if it was minus f of x, it would be flipped upside down like so. The next kind of transformation we can have is to either add or minus something, either inside the brackets or outside the brackets. If you were to do it inside the bracket, what would that mean is that you're going to translate the graph, let's say move the graph minus or plus a in the x-axis. Now this may seem counterintuitive. If you have add a in the bracket here, why should you move minus a in the x-axis? That is to say, you would move left if it was a positive number in here. Well, again, what we're saying is if we use that example of x equals 1, we're now saying rather than having the y-coordinate associated with x as 1, at x is 1, instead, let's say a was 3, you would be looking, well, what's the y-coordinate at when x is 4? What is the y-coordinate when we are 3 more than our current one? Well, that would then take the y-coordinate that is meant to be at 4 and bring it over to the left to be above where x is 1, and thus everything gets shifted to the left by that 3. Alternatively, if we were to put it on the outside here, this is now as you would expect. So you would take the y-coordinate that you'd expect to get from that given x, and then you would either just add that 3 or minus that 3. So in other words, here we would translate plus minus, again the same way around this time, a in the y-axis. So inside the bracket is moved left or right, the opposite way. Outside of the bracket, you would move up and down the same way around. Then lastly, you could multiply, again, either inside the brackets or outside of the brackets. What we're going to say this does is it stretches the graph. And also, once again, because just like with adding or minusing inside the bracket, here, this is going to be slightly counterintuitive. So what we'll say is that we would stretch by a factor of 1 over a in the x-axis. And again, the reason for this is if we were to, let's say, have our x-coordinate be 1 and a is now going to be 2. So, well, what is the f of 2x? The y-coordinate above x is 1, therefore, is now going to be the y-coordinate that otherwise would have been above 2. If we then took x as 2, the y-coordinate is going to be that coordinate that otherwise would have been above x is 4. If you take x is 4, then that y-coordinate is going to be the y-coordinate that otherwise would have been above x is 8. So essentially, we are squeezing the graph together towards the y-axis. It's a stretch of 1 over whatever this number is. If in turn this had been a fraction itself, let's say this was the f of a half x, 1 over a half is the same as 2. So you would then be doubling every x coordinate. The key here, as it is with any of these transformations, is that the coordinate in the axes that you're not affecting stays the same. So here, because we're affecting the x-axis here, all of the y-coordinates remain as they otherwise would have been. All you're doing is just shifting them either to the left or the right, either closer together or further apart. Then again, just counter to that, if we'd put the multiply the coefficient in front of the fx instead, we're now going to be stretching in the y-axis. And again, as with adding or minusing on the outside, this one is now as you would expect it to be. So here, it was just a factor of a in the y-axis. So if it's 2f of x, then every x coordinate stays the same, but all the y's would be doubled. If it was a third f of x, all the x coordinates would stay the same, but the y's would be times by a third. These then are your array of transformation options that you can choose from. Either that you are going to have to recognize as what's happening, or they'd ask you to sketch this version of this based upon an original y equals fx that they have given you. And just to be clear, when they do say sketch, all they're mainly looking for is the correct shape with maybe the coordinates where it cuts the x and y axes. You don't have to be absolutely precise, so just as long as you're getting across the right idea. Just before we get to an example question of that though, it may make sense to also just go over what the general shapes of certain equations are. If you are looking at an x squared graph or a quadratic graph, for a positive, that is going to make a parabola, a U shape. Again, this may be stretched or moved in any way, but this will be the overall shape. Whereas a minus x squared, then other stuff following it, would be a negative parabola. It's more of an archway or an N. If, however, your first or highest power is a cube, then we're going to make this kind of shape here. So think of it as starting from the right going left with the regular quadratic curve, but then come down again on the left. Meanwhile, the minus, again, will just that be flipped. So start with what the negative quadratic would have been, going from the right towards the left, but then come up again once you've reached that left-hand side. Meanwhile, for the likes of 1 over x, or the square root of x, we're actually first of all just probably going to want to just put up some axes just to give a point of reference, because these do have to exist within certain regions. If it was just a singular 1 over x without any plus or minus in any degree, what this is going to do is in the top right-hand quadrant, we're going to start high up, close to the y-axis but not touching it, coming down steep, but then level off before we touch the x-axis. And that will be the inverse of that in the bottom left. So starting steep here and then become shallow on the left towards the x-axis. Meanwhile, if it was the square root of x, then that's only going to exist in the top right quadrant because you can't have a square root of a negative x value. That's going to start off somewhat normally, but then it's going to level off as you go further and further right. Meanwhile, for the natural log, again, we may just want to put up some axes like these. It's going to start close to the y-axis in the bottom right quadrant, and then it's going to come up through the x-axis and level off here, and that coordinate specifically is going to be 1, 0. And then finally, just to acknowledge it, the equation with just an x, that's just going to be a straight line, right? That could be going positive gradient, negative gradient, doesn't matter. If there's just a power of 1, it's just a linear equation, what you should already be familiar with from straight line questions. All right. With all of that established then, let's, look at this question here on the right. So here we are given an equation for fx. This is expressed as a product of 3 brackets, here being x plus 1, x minus 2, and 3 minus x. Now, based on this function, the question would like you to sketch the graphs for f of x, f of x plus 3, and then minus f of 2x. So as we can see here, we're now starting to get into territory of combining multiple transformations together. And then when you've done that, you also have this puzzle on the right. Now this is more for people who are either already in A2 or who may have already done the differentiation while still in AS. You may have done it before, did transformations, possible. But yeah, just more worry about this question if you have done differentiation. Don't worry too much if you haven't. But either way, we're now told to find the transformation that makes the minimum of this original graph here 1, 0. Just a heads up, when you're doing that, I'm going to suggest that you round your figures to 2 decimal places. In general, you shouldn't actually need to go into that kind of degree of accuracy with those kind of questions, but here all the same, it should just be a good practice for how to apply these transformations yourself. So, I would also suggest that while it is useful to have this equation in its bracket form and to think about why that might be useful, you're also probably going to want to expand them, again to get you yet more information about the original graph. You may even want to sketch that original graph just as a reference point. But either way, from that, then think how can we, based on these descriptions, make these transformations here, and again, what would have to be done to do the right-hand side. So, pause the video, just have a go at sketching this out for yourself, and then press play again when you're ready to compare. Okay, so to start off with, the reason why it's useful to have your original equation in terms of these brackets is that they can tell you the roots of the equation, the solutions, the points where it crosses the x-axis. Because if we were now to say that this equaled 0, that it had no height, we just said, well, one of these brackets must be 0 in and of itself. So in our case here, that could be that when x is minus 1, because then minus 1 plus 1 is 0, makes the rest equal 0. So let's just say that minus 1 is about here. And then here it could also be that when x is 2, because 2 minus 2 is 0, makes the rest 0. So that's going to be about here, so 2, 0. And then here, this would be when x is 3, because 3 minus 3 also becomes 0. So that would be 3, 0 here. As for our expansion of this, if we were just to say times out the first couple of brackets first, you should get x squared minus x minus 2, and then that's still being times by the 3 minus x. Therefore, to times this out as well, you should end up with minus x cubed plus 4x squared minus x minus 6. Now, what expanding the brackets has given us, therefore, is 2 pieces of information. Firstly, is the shape that this graph is going to take. Because we know it's a negative cubic, we know it's going to take this shape from down here. Then secondly, it's also told us what the y-intercept is going to be. Because when all of these x's are 0, it will cut the y-axis. Well, if all these are 0, that just leaves us with minus 6 here. It's like how when you do your y equals mx plus c, that last digit on its own is the y-intercept. So we know that it's going to be crossing, let's say for the sake of scale, well, for what we're going to have to do later, that this here is just our 0, minus 6. Then, with this information, we can now go about just trying to sketch the general shape of the graph. Again, it's just a sketch as long as it's the correct shape going throughout the points. Don't have to worry so much about how steep it is or so forth. So let's say that we're going to come up through this point here, then back down again. This will then come through this coordinate here, and then up this side here. This is our general y equals the f of x. Now that we have this, we can start trying to sketch on our other lines. So if we're now to do 4 f of x, then we're saying that all of the y coordinates are going to be times by 4. Well, in the case of what cuts the x-axis, 0 times 4 stays the same. So actually, we're going to go through these exact points in the y-axis. However, here, this 0 minus 6, that's now going to go all the way down to be a 0 minus 24. And of course, even though we don't know the exact coordinate of this point here, we are going to be quadrupling it, so it's going to end up somewhere up here. Therefore, we're now at the very least going to be steeper than the previous line, just coming up from this way. We're going to come up to a higher point. It's going to come down through here, through that point, already turning back up to go through here, and now carrying on steeper. This is our y equals 4 f of x. As for the f of x plus 3, well, again, if it's a plus in here, we'll think of it as a translation of a negative, so we're going to move 3 to the left. So in each case, so this 3 is going to become a 0 here, or with the 0, 0. This 2 is now going to be where the minus 1 is, and the minus 1 is going to be all the way down here at minus 4. Meanwhile, as for what was the y-intercept, the 0 minus 6 here, that 0 is now going to become a minus 3. Well, minus 6 stays the same. But because that's no longer now the y-intercept, that's just now in this space over here, we don't have to worry about marking it. And in fact, we don't have to worry about coming up with another point at all, because we already have the y-intercept. The fact that this 3, 0 here has become 0, 0, that's cutting the y-axis as it does the x-axis. So we already have now just these 3 points here. Thus, if we now just try to recreate the original curve to try to be as similar to that one as possible, because all we've done is shifted it to the left in theory. So if we start from down here and come up through your 0, 0, then curve back down about the same height as we did here for this point here, then come down to about the same level as you had for here before coming back up and continuing on this way with that line in theory being parallel to this line here. That is going to be a y equals the f of x plus 3. Which then finally takes us to our compound transformation here. The fact that we're putting a minus in front of the fx, but also making it 2x. So we may wish to, well, we could deal with this in either order. I'm going to choose to just first of all focus on the x values. Because here it's now 2x, just like here with the a in our rules, when it's ax here, you'll stretch by a factor of 1 over a, in this case 1 over 2. So we're now going to halve each of the original x coordinates. Again, remember, we're always going back to the original line when we do this. So this 3, 0 is now going to come here to be 1.5, 0. This 2 is now going to be 1, 0. And this here is going to become minus 0.5, 0. The y-intercept stays exactly the same because half of 0 is still 0, and again, the y-coordinates are unaffected. That is until we introduce this minus now out in front. Because now for that, we're going to reflect in the x-axis. We're going to flip it upside down. Now it's the turn of these x-axis coordinates to stay the same, because flipping 0 in the y does nothing. But this 0 minus 6 is now going to come up to the top and become 0 positive 6, like so. With this in mind, the entire thing is now flipped upside down. We now know the coordinates of intersection. Therefore, we can then just try to recreate the curve as best we can. So coming down from here, turn around here, come down here, and then carry on through down this way. We've squeezed everything towards the y-axis, halved all of the x values, and then flipped the graph upside down for that minus. So, if these were all of your sketches, then that just leaves us with now trying to figure out this other puzzle here of finding the transformation that makes the minimum point 1, 0. As I said before, if you haven't covered the topic of differentiation yet, don't worry so much about this. If you have though, again, I also advise that we round our values to 2 decimal places just to make things easier for ourselves. If we're talking about the minimum, that indicates to us that we're going to be looking at the differential, so when the dy over dx equals 0. So if we just differentiate this expression, use a quadratic formula to find out what x values it'll equal 0 for, and then plug those back into the original to get y values. Again, specifics on that in the topic of differentiation itself, if you haven't covered that yet. You'll find that we should have a maximum point here of approximately 2.54 and 0.88, and then a minimum point around here-ish of 0.13 and minus 6.06. So how are we now going to use these with transformations to turn the minimum point into 1, 0? Well, now, regardless if you've done the differentiation or not, we can again think about these transformations here. So if we are trying to get this point again, because this is right now the minimum, if we're presumably going to try to make this into the 1, 0, what we could try to do is we're going to want to move this graph to the right and then up. So to move the graph rightwards, we're going to need to have x minus, because remember it's counterintuitive. So if we want to add in the x-axis into minus in the bracket, and what do we need to move it right by to make it equal to 1? Well, that's going to be 0.87. But then afterwards, to then move it up, we'll just then need to add 6.06 to bring that then up to the 0. Okay? That would be one way of making this minimum point here into 1, 0. Alternatively, however, if you were so inclined, you could actually also make this maximum point here a minimum here. All you would have to do is reflect the graph in the x-axis, as we've seen here when we did that in our third sketch. Putting a minus in front would bring this point down into the negative region here. So if we were to do the minus of f, so that's so far bringing this upside down. If we're now wanting to move this to the left to turn the 2.54 into 1, we are now going to have x add. What do we want to do to turn it into 1? We'll just add the 1.54. And then again, because this is now a minus 0.88 because it's a negative, we'll have to add 0.88 here. That too would actually make a minimum at at coordinates of 1, 0. Okay? So that is just how we can apply different transformations to a given equation, and how potentially we can also figure out what transformation would have to be applied to make a certain thing true. With this in mind, we're now going to just move on to that other concept I mentioned before, that of the modulus, this now just being purely within A2. So, fundamentally, the modulus is something which turns all negatives positive. So if we were to just have a graph here, let's just say it was a straight line graph doing this, right? Now the modulus we're going to represent by putting 2 vertical lines on either side of whatever thing we are making all positive. So if you have put this around the x value itself, this means that any x value that is already positive is unaffected. So anything on the right-hand side of this graph is not going to change. This will remain looking like this. However, any negative x values are now going to be turned positive. So if it was a minus 1, we're now going to imagine that it's like the positive one. Well, what was the y coordinate at that point? Minus 2. would become like positive 2, or what would the y coordinate of positive 2 be? Basically, it's like doing the f of minus x, but only applying it to the negative values. And so, what you end up with is a reflection, or kind of like a line of symmetry in the y-axis. It now becomes, in this case, a v like so. So say the positive x values all stay the same, but now the negatives just become a reflection of those on the left-hand side. Meanwhile, if the modulus symbol had been put on the outside of the function, now it doesn't matter what the x value is, but any negative y value is now what would become positive. So here to start off with, again, all of these are already positive y values, so they're not going to change at all. However, from here, all of these would be negative, but now basically we're just going to remove the minus sign, meaning that they are now going to be coming up like so here. So yes, if the modulus sign is around the x, then the negative x values just become a copy of the positive x values. If the modulus is around the function itself, or the entire expression, then it's the y values that are going to flip up into the positive. To give an example of this, if we were to sketch y equals the modulus of all of 4x minus 3, and stating where it cuts the axes, and then from that see if we can find the set of values for which the modulus of 4x minus 3 is greater than 2 minus 2x, and then finally the modulus of 4 minus 3 is greater than 3 over 2 minus 2x. For this, actually no, first of all, we might make these axes just a little bit bigger, just so we can zoom in a little bit more what we're going to be drawing. And then if we were to try to sketch on just this modulus graph here, right? So again, because it's a sketch, we're just looking to get the general shape. Usually, we would be having that it's a straight line, first of all, because there's only a power of 1 on the x. It's got a gradient of 4, and would usually be going through minus 3 in the y-axis. So it would usually just be coming down this way, something like this, and it would then usually carry on to go through 3 here. But because we're now doing the modulus of the entire expression, this is like saying the modulus of the function, so as soon as we hit the x-axis, we're instead now going to reflect up this way, where now this coordinate here is 3 over 4, 0, because, well, where would this equal 0? That would be if x equals 3/4, because 4 times 3/4 is 3, 3 minus 3 is 0. This is the minimum point we're now going to have before it now rebounds upwards towards the left. As for where it then cuts the y-axis, well, usually if there hadn't been for the modulus sign, then we'd just say, okay, well, 4 times 0 is 0, so minus 3 is minus 3. It would usually cut at minus 3, but now that minus goes away, so it's going to cross at just a regular 3, 0. Now that we have this, we can start comparing this to these other line expressions here. If we were to look at 2 minus 2x, again, this will be a straight line because it's just x to the power of 1. It's minus 2, so it's going to be a negative line coming down. And then if we just wanted to work out, first of all, where that cut the x and y axes, just so we have a reference point to make sure we're drawing somewhat accurately, if we were to put x equals 0 here, you'd have 2 minus 0, there's still 2. So we're going to be crossing at 2, 0 here. Then as for making the whole expression equal 0, you'd have so 2 minus 2x equals 0, so 2 equals to 2x. Therefore, x is going to equal 1 where it crosses the axis here. So it's also going to cross here. Therefore, we're going to have a straight line that cuts through these 2 points here and comes up the other side, carry on like so. So as we can see, most of this modulus function here is above this line here. However, because there is this tiny corner here that is below, we can't just say that it's always going to be true. So we need to work out specifically what range of x values does that work with. The way you're going to do this from a calculation standpoint is you are going to square both sides of this inequality. And why this works is, as before, because the modulus sign is basically negating a minus sign, we don't know if this is actually positive or actually negative. By squaring, that takes that ambiguity out of the equation, because a positive times a positive is positive, and a negative times a negative is also positive. It means that we don't have to worry about it. So here we can just say that 4x minus 3 squared is greater than 2 minus 2x squared. So here, if we just expand those brackets, 16x squared minus 24x plus 9 is greater than 4 minus 8x plus 4x squared. Bring that all onto the left-hand side. You're going to end up with 12x squared minus 16x plus 5 is greater than 0. This you can factorise, so to make it 6x at the start of one bracket and 2x at the start of another. If we then make this a minus 1 here and a minus 5 here, because 6 times minus 1 is minus 6, and minus 5 times 2 is minus 10, minus 6 minus 10 makes the minus 16 in the middle. This is still greater than 0 here though. Now, usually, if this was just equal 0, you'd look at what x values make the bracket equal 0. So in this case, that would be 5/6 here and a half here. But because it's greater than 0, we're going to, as we can see here, we're looking to be on the left-hand side of the lower value and the right-hand side of the upper value for this to be true, for that modulus function to be greater. Therefore, we'll say that this is true if x is less than the lower value, which is the half, or x is greater than the upper value, which was the 5/6. And again, if you wanted, you could just test out some the x values in here to see if that's true. When you want to do this in your calculator, the button for the modulus, if you're unaware, is the button which has ABS on it, on certain models of calculators at least. Okay, so that would be for that scenario. What if, though, we're looking for it just to be greater than this other expression here, so the 3/2 minus 2x? Well, in a similar manner, let's work out when it's going to cross the x and y axes respectively. If we put that x is 0, then we're just going to have 3/2 minus 0, so that just remains 3/2, so 1.5 essentially, so that's now going to be just below that in turn. And then here, if we make this equal to 0, so 3/2 minus 2x equals 0, so 3/2 equals 2x. Therefore, your x is going to equal 3/4. So it crosses at 3/4 0, exactly where the modulus function did. So again, if we want, draw on this line going this way, again, just showing why it's not perfectly to scale, because these are meant to be parallel, because they're both minus 2x. Well, here, almost the entirety of this line is above what is now the blue, the 3/2 minus 2x. It's not entirely above it, though, because they do share this one exact point. We're on the same spot. So while the modulus isn't less than it, they are equal to each other, which is not the inequality that we're looking for here, so that is a contradiction. So rather than, though, having these inequality signs to say when it's not true, what we'll say is that what set of value do we have for x for which the modulus is greater than that equation? Well, that's when x is anything other than 3/4, because when it is 3/4, they are the same thing. Okay? Does that make sense? If we're good with that, let's again just have one other question. We'll see how you get along with for yourself. So we now have a graph like so, which is, to be clear, or just the regular function though so far. The modulus has not been applied yet, which is made up of two straight lines that meet at a point here, q, 6 minus 1, and then cross the y-axis at 0, 11. So this is just the y equals f of x. To be clear, we haven't applied a modulus explicitly to this yet, although as we may find later, there could be one in the equation of x itself. Again, we don't know what that x equation is. All we know is this is your original curve as is, and then based on this, now sketch, I'll do it on these axes here, but throw up some axes of your own on a piece of paper or something. So then sketch what the y of the modulus of this fx would be, and then also, just to make sure we're not forgetting what we discussed on the previous screen, y equals 2 f of minus x plus 3. And each time give the coordinates of p and q. And then once you've done that, given that the actual equation of fx is indeed has a modulus in it, that it's a times the modulus of x minus b minus 1, find what a and b must be therefore. So have a go at sketching first of all, both in terms of think how we're going to apply modulus and how we're going to apply these combinations of the previous transformations all together. And then, yeah, think about what possible transformations must have happened to have turned this, or to have turned some more regular equation, let's just say of x, into this. Pause the video, have a go for yourself, and press play again when you're ready to compare. To begin with then, first of all, if we are just taking the modulus of this, and the modulus is out around the entire function, as we can see from the example before, this just means that anything that would otherwise be negative in the y direction is going to become positive. So anything that was in the positive y direction anyway stays the same. So this is still going to be like this here, and this would still then be like this here. So this is still going to be going through 0, 11 here. The p hasn't changed. But this little negative corner here is now going to flip up into the positive here, where again the x coordinate will stay the same here, but now that negative y will become a positive, so it just becomes a coordinate of 6, 1. Then, as for doing these transformations here, if first of all we're going to be doing the f of minus x, this was where we flipped in or reflected in the y-axis. So this is now going to come onto the left here to become minus 6 minus 1. Then all of your y coordinates are going to be doubled, and then they're going to have 3 added to them. So here, if this is now becoming minus 6 minus 1, to times by 2 would then become minus 6 minus 2. And to add 3 to that, minus 6, positive 1. Point, therefore, we can sketch as being somewhere over here, so you're 6, 1. Then as for the y-intercept, obviously doing a minus 0 is not going to make a difference. So if we then times the 11 by 2, that's 22, and add 3, that brings it up to 25. So if we just label this here as our 0, 25. Again, because it's a sketch, you don't have to make sure it's exactly double plus 3, it's just as long as it's labelled correctly. If we then just join up our dots here in what would be the V shape that it should have otherwise, your graph will therefore now look like this. As for then, just finally working out what transformations, or what must A and B be in order to give a graph this shape here, what we're going to be thinking about is, well, what would the original graph have been? The original would surely have just been your fx equals x, and it's had all of this stuff then added onto it. So to just sketch out what originally the graph of, well, the fx equals the modulus of x. Let's start from there, because we'll just already have the modulus function. That's going to look simply like this, right? Because f of x equals x, y equals x is just a diagonal line going straight through. So now this negative will come up into this region here. So we're crossing at 0, 0 for our minimum point here. So again, this is fx equals modulus x. Now, what transformations are going to turn this into this? Well, we need to somehow move this minimum point 6 to the right and then 1 moving down. To the right is more straightforward because there's only one part of this equation that affects the x direction, that's the minus b, and also that makes sense because if we're moving right, that would be adding, so this will now be a minus in the equation. Because we want to move 6 to the right, it will be x minus 6, therefore we can say that b equals 6. Now then, as for the y-coordinate, the a would be applied first, and then the minus 1. Just think about like BIDMAS or BODMAS, whatever acronym you have learnt. The multiply comes before the subtraction. So we're going to times by a before we minus 1. Timesing by anything to 0 though in the y direction, that's not going to do anything. That doesn't tell us anything. So we're going to have to look to the point that's going to become p, therefore. Right now, because the f of x is just the modulus of x, the y coordinate is just going to equal whatever the modulus of x is. So this point previously, which is now going on to become that p here, that previously would have existed at -6. Therefore, this the y coordinate here is also going to be 6, so -6, 6. So by translating this graph 6 to the right, we have now brought this point that will become p to 0, 6. So how are we going to turn that into 0, 11? Well, what we could do first of all is to times it by 2, because that would then make it 0, 12. Well, that's not the same, but then, don't forget, we're minusing 1 afterwards. 12 minus 1, that gives us the 11. And also here, this 0 to become -1 as well. So, in general, we're saying a, therefore, must equal 2. Again, this is ultimately the answer we're after, but if we just want to reiterate so we can visualize it for ourselves, we're therefore saying that for this above equation, fx equals 2 times the modulus of x minus 6 minus 1. If we just want to double check, so if we, to make this coordinate here, so x is 6, so 6 minus 6 equals 0, the modulus of 0 is still 0, 2 times 0 is still 0, minus 1, y coordinate of -1. Great. As for this other one here, x coordinate of 0, 0 minus 6 is -6. The modulus of -6, we just remove the minus, becomes +6. 2 times +6 is 12. -1 is the 11. Yep, we've got it. These are our A and B for this modulus and transformation question.